Okay guys, this is Earth Science, Chapter 26, Worksheets, and end of the chapter assessment. This video covers the worksheets and the end of the chapter. The other ones are looking at the questions at the end of each section. So you'll want to check that out too. Okay, so we have the sun's size, heat, and structure. So let me play this little. So as you can see on the photosphere, it says that it's 3,500 degrees Celsius. It is a high magnetic field. It runs on an 11-year cycle. Because the sun is not solid, its rates of rotation varies. The numbers near like sunspots and 11-year cycle are going to refer back to the end of the chapter assessment. Okay, so when I'm going over this, this slide, you should be looking at your worksheet. Okay, so some of it doesn't seem like it makes sense, but if you're looking at those worksheets, it does make sense. Okay, so make sure you have your worksheet out 26.1 and you're looking at it. Okay. Whoops, hold on guys. Okay, let's go back here. Okay, so again, we're on the worksheets. Solar wind, and it will refer to number 1 on the end of the chapter, but constant stream of electric charged particles given off from corona, increased by coronal holes and solar flares. I'm going to skip the video on that because I'm having a little bit of a challenge doing those. Okay, again, we have magnetic storms. So solar wind increased by coronal holes. Solar flares lead to electrical charge. Then it's going to ask you about the 6 layers. So there are 6 layers. This is at the bottom of your worksheet. You have the core, hydrogen, helium, and plasma. 2 radioactive zone, plasma. Convection zone features moving currents of plasma that carry energy to the sun's surface. Photosphere, visible surface of the sun. Chromosphere, inner layer of the atmosphere. And C, corona, edge of the sun's atmosphere.
Nature, along with a tremendous gravitational pull and an extensive magnetic field, helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere, the photosphere, the convective and radiative zones, and the core. In terms of atom count, the sun is about 91% hydrogen, the sun's fuel, 8.9% helium, and 0.1% heavier elements, such as carbon and nitrogen.
Okay, so now we're in section 26.2, observing the solar system, a history. So you should have your 26.2 worksheet. Ptolemy thought that planets went around the Earth. Copernicus believed that planets orbit the sun. Tycho observed moon and planets in orbit. Kepler had 3 laws: elliptical planetary orbit, equal area law, harmonic law, and Mercury. So see where it says harmonic law, then it has parentheses 11? That's just reminding me and you that that's going to refer to the end of the chapter assessment. Okay, so when you see those numbers throughout the slides, you know that it's a reference to the end of the chapter. Okay, Newton came up with the law of gravitation and 3 laws of motion. Okay.
In Central America, Mayan astronomers who built
I'm going to skip some of this here.
Polish cleric weren't published until after his death in 1543. Enter Tycho Brahe, the Danish astronomer, who proved in 1577 this comet was farther away than the moon. Brahe lost part of his nose in a duel and wore a golden prosthetic. It didn't hinder a brilliant career. His precise observations established a real understanding of how the planets orbit the Sun. Working with Brahe, the German Johannes Kepler defined 3 laws of planetary motion. The first was that planets move around the Sun in ellipses, not circles. The second was that orbital speed varies. The planet travels fastest when nearest the Sun, and slowest when farthest away. His third law was that planets orbit slower and slower the more distant they are from the Sun. And here, with Earth's orbit overtaking that of Mars, Kepler explained those retrograde loops.
Is that the Leaning Tower of Pisa?
Yes, and it is where the great Italian mathematician and astronomer Galileo Galilei first worked. He turned the telescope, a Dutch invention weaker than modern binoculars.
Okay, let's go to the next slide here. Back on your worksheet, elliptical orbit. Planets have elliptical orbits. Okay. Equal area law. Imaginary line from planet to sun with equal space and time. You can see it seems to go faster when it's closest to the sun. Okay, harmonic law, time it takes a planet to complete its orbit. Okay.
Kepler's first law of planetary motion states that all planets move about the Sun in elliptical orbits, having the Sun as one of the foci. But what does that actually mean? Well, an ellipse is a shape that resembles a kind of squashed circle. Its foci are 2 points within the ellipse that describe its shape. For any point on the ellipse, the sum of that point's distances to the 2 foci is the same. The further apart the foci are, the more squashed the ellipse is. If the foci become so close that they are only one focus, you just have a circle. In reality, orbits are never perfectly circular, but we do know that the Sun will always be one of the foci of the elliptical path of an orbit. Knowing that the Sun is a focus of the planet's orbit can tell us a lot about the shape of that orbit. Kepler tells us that orbits are ellipses, which are like circles with some added eccentricity. But what is eccentricity? How do you figure it out? Eccentricity measures how flattened an ellipse is compared to a circle. We calculate it using this equation. So, what does that mean? Well, A is the semi-major axis, or half the distance along the long axis of the ellipse, and B is the semi-minor axis. or half the distance along the short axis of the ellipse. The equation is a way to compare these axes to describe how squashed the ellipse is.
Okay, let's move on. Getting a little too technical there. Okay, so this is a vocabulary review and concepts review. Now you are on the end of the chapter, okay, assessment. Okay, so what I did was I put the vocabulary words that will be an answer, okay, but I kind of mixed them up, so you're going to have to put them into the correct blank, okay? So you're going to do that for 1 through 5. And then number 6, what's the difference between plasma and gas, okay? So you can find that on page 572. What is some of the evidence for the sun's rotation? I had mentioned it earlier. It's on slide 2. Number 8, why does Mars appear to move backwards? You'll see that on slide 8. Okay, so it's kind of like when you're driving in a car and it seems like you're passing the moon. It's not really moving backwards. It's just that you're going faster. Okay, you're moving away. Number 9, I have to go back and get the book. I don't have it with me. I should have brought it. But so I must have been stuck on that one. So if I can read it later, maybe text you guys or something. Number 10 is on slide 8. Okay. 11 is on slide 9. 12. Maybe another one I got stuck on. 13 is on page 575, first paragraph. 14, what makes an apple fall when tossed in the air? So this is me giving you a clue to the answer, okay? Number 15 is on page 572. 16, how would Earth be different with weaker magnetic field? So I cover this more in the other videos. And basically, the Earth has a magnetic field that protects us from the sun. And so if it was gone, we would be more like Mars, probably. Okay, so that is how we are protected. Okay, so you can give some examples of how that would hurt species, and then also weather, climate, those kind of things. Think of maybe global warming. Okay. 17, sunspots vary on 11-year cycle because, and that was slide number 2. Okay. So the graphic organizer, use the following words to fill in the graphic organizer using some of these terms. So again, I've given you the terms that go into those circles on the graphic organizer, but you just have to figure out where they go. And then I put like 1, 2 of them in there that don't belong, so you'll have to eliminate those 2. Okay, I think it won't be that bad. Okay. All right, interpreting diagrams. Okay, so this one I thought was kind of hard. It might not be 100% correct. So if you come up with something else, that's just fine, okay? It says 18, which phases look the same but have moved? Okay. So I've got to get the book. You guys, you just have to wait 30 seconds. I got to get that book because I'm not sure. Okay, hold on a second. Okay, guys, sorry about that. I just forgot to bring the book in here with me when I started this video. And I'm not good enough to edit, so you're just going to have to bear with me, and you could fast forward over my rambling, okay? Let's see. Okay, now I'm on the review. Okay, so number 18 says, All right. Which phases in figure B match phases 1, 2, and 3 shown in figure A? Okay, so to me, it looks like figures 1, 2, and 3. Okay, because it's just the 8, 7, and 6 are just the opposite, and figure 1 is 1, 2, and 3. Okay. Number 19 says, when Galileo looked at Venus with his telescope, he saw Venus in phases that are impossible in the geocentric system shown in figure A. What phases did Galileo see? Okay, so again, a little confusing to me. I'm not 100% sure, but for me, it was looking at 1, 2, and 3, and I don't know. If you guys come up with something else, that's great, okay? Or talk to Mr. Fideli about it if you have questions. 20. Why did Galileo's observations of Venus help to disprove the geocentric model of the solar system? So it was Galileo's observation of Venus that proved the theory. Using his telescope, Galileo found that Venus went through phases just like our moon. But the nature of these phases could only be explained by Venus going around the sun, not the earth. Okay, so a long time ago, people thought that everything went around the earth. And then later on, through Galileo's observations, they learned this wasn't true. Okay, 21. Are there other planets that would show phases as Venus does? Explain. So the two inferior planets, or inside planets, the ones that are closest to the sun, Mercury and Venus, which have orbits that are smaller than Earth's, exhibit the full range of phases, as does the moon when seen through a telescope. Okay, so let's go back to, this was fine. Let's go back to number 9, because I skipped that. What surface feature indicates that the sun's inner layers are in motion? Okay, so I was kind of a little confused. I felt like it was sunspots, but then I was like, maybe it's solar winds. So maybe you guys can read those two and determine what you think, okay? Number 12 was the graphic organizer, okay? And so that's on the graphic organizer right there, okay? Let me read the question to 13. It says I know I didn't do this one. Okay, so this is a math one, okay? So this will be a challenge. The average speed of the coronal solar wind is 450 kilometers per square. How long does it take a particle in such a wind to reach Earth? Wait, that's 13, my bad. 12, let me go back. 12, no, wait. All right, actually, we're good. I'm sorry. Okay, so, do you guys have any questions? You'll text me, let me know. Sorry the video was a little rough, okay? I'm going to get better, hopefully, at presenting this information. I hope to see you guys soon. I miss you guys. Talk to you later. Bye.